Hey everyone, and welcome to this section, where we explore tools, toolkits, and agents. You may remember that at the start of the course, we introduced LangChain as a framework for developing LLM-powered applications that are context-aware and can reason. We already achieved context awareness through the retrieval-augmented generation technique, which included indexing custom data, embedding a user's query, retrieving the text semantically closest to the query, and having an LLM construct a response based on the query and the retrieved data. Now, we'll learn how to create applications that can also reason, referring to the ability to choose and order the steps necessary for completing a task given a set of tools. The chains that make this behavior possible are called agents. Agents differ from the chains we've constructed so far in that they're not anchored to a predefined sequence of steps. Instead, the tools and the order in which they're applied are task-dependent. This may sound a bit too abstract, so let's consider a simple example. Imagine we supply a chatbot with the following tools, responsible for 3 very different tasks: a Wikipedia tool, helpful in searching the Wikipedia page; a retriever tool, appropriate for retrieving data from the Intro to Data and Data Science course; and a custom Get Python version tool, implemented to retrieve the version of Python used in the current environment. Let's say we now ask the agent-equipped chatbot, "Could you tell me the version of Python I'm currently using?" It'll utilize its large language model to determine the most appropriate tool to solve this task. As you've already guessed, that would be the Get Python version tool. Let's now task the chatbot with something a bit more challenging. For example, I'm currently following the Introduction to Data and Data Science course. Could you list the programming languages a data scientist should know? Additionally, could you tell me who created them? To complete this task, our chatbot splits it into 2 more manageable components, namely, retrieve the relevant programming languages from the course with the help of the retriever tool, and then utilize the Wikipedia tool to look up their creators. In the practice lessons to come, we'll implement this same chatbot, answer the same questions, and trace the model's thought process. I hope you're excited about that because I certainly am. But before jumping into coding, let's first talk terminology. See you shortly. Welcome back, everyone. In the last lesson, we introduced these interesting chains called agents, specifically implemented to create reasoning chatbots. Given a task and a set of tools, they'll choose and order the tools they need to complete it. In this lesson, we'll dig a bit deeper into the mechanics of agents and introduce some relevant terminology. Let's get started. The components required for creating reasoning chatbots include the following: tools and toolkits, agents, and agent executors. Let's start with tools. Tools are LangChain interfaces, each equipped with an intuitive name, a thorough description, a JSON input schema, and a corresponding function. When an LLM chooses the appropriate tools for a task, it does so based on their name and description. This highlights the importance of writing these properties to convey the tool's purpose as precisely as possible. For example, a good name for the Wikipedia tool introduced earlier would be, well, Wikipedia. To instruct the LLM when it should use this tool, we add a helpful description, like the following: a wrapper around Wikipedia, useful for when you need to answer general questions about people, places, companies, facts, historical events, or other subjects. Input should be a search query. The input schema is a description in JSON format containing the name and type of the parameters we should pass to the tool. For example, the input schema for the Wikipedia tool could look something like this. It tells us that this tool expects a single input value, query, described by a title and a data type. Finally, the function associated with a tool can be anything from an API wrapper, like a wrapper around the Wikipedia API, to a retriever, like one extracting information from a 365 course, to a custom-defined Python function, such as one displaying the installed version of Python. So far, so good. Next in line are toolkits. These are a collection of tools designed to be used together, kind of like in a regular toolkit. For example, the GitHub toolkit is equipped with several tools, some of which include fetching an issue from the repository, posting a comment on an issue, or creating a new file in the repository. Another example would be the Slack toolkit, containing 4 tools: one that gets a channel, one that gets a message, another to schedule a message, and a 4th one to send a message. We won't dig too deep into the topic of toolkits, but feel free to explore the available ones in LangChain's documentation after this lesson. Very well. Once all tools are well defined, equipped with a function, a JSON schema, and an explanatory title and description, they're ready to pass to an agent. Agents are specially constructed chains that can choose among a set of tools and determine their order of execution to provide custom solutions. An agent chain typically consists of a prompt template, an LLM, and an agent output parser. The prompt template expects a dictionary with 2 key value pairs, the user's input, and all intermediate steps, if any. Intuitively, the purpose of the intermediate steps is to keep a record of the actions executed so far and the results of these actions. This knowledge is necessary for the second agent component, the LLM, to determine the next action in the sequence. Finally, we arrive at the agent output parser, whose task is to parse the LLM decision in one of 3 forms, depending on the situation. If the LLM has suggested a tool to continue the solution in the next step, the agent output parser will return an agent action object. If the LLM has suggested more than one tool, the parser will return a list of agent actions. And if the task is completed and no further action is required, the parser will return an agent finish object, holding the final response. It now becomes clear that the agent chain is not responsible for executing the actions. This is left for an agent executor to handle. In LangChain's documentation, you can find an intuitive pseudocode explanation of how this object works. Let's try to break it down into digestible steps. The agent executor's first task is to invoke the agent by passing the user's query as an input. The output can then be an agent action, a list of agent actions, or an agent finish object. In the pseudocode, the output is stored in a variable called next action. The following part of the agent executor checks if the action suggested by the LLM is to return a final response to the user. If not, then the following steps are executed. First, we run the action. That is, we execute the tool with the input, all specified in the agent action object. The result from this execution is referred to as an observation. Next, we update the next action variable by invoking the agent anew, feeding the user's query and the intermediate steps. Based on this information, the next action is determined. If it happens to be an agent finish, the result is returned to the user. And that's how the process goes on paper. Currently, this might still seem a bit abstract, but don't worry, we'll dedicate the rest of this section to creating tools, agents, and agent executors in code. So buckle up and let's jump right in. Hey everyone! In the last lessons, we introduced tools, toolkits, agents, and agent executors, and explained how they all partner to create a reasoning chatbot. In the upcoming sessions, we'll realize all the examples introduced so far in practice. The game plan is as follows. First, this lesson is dedicated to the runnable nature of LangChain's tools and how we can pipe them into a chain. For this demonstration, I've chosen to use the Wikipedia tool. After that, we'll spend a lesson creating a tool from a retriever and one from a custom Python function, returning the version of Python used in the current environment. Next, we'll cover agents and agent executors. Once comfortable with these objects, we'll solidify our expertise in agents by creating one ourselves, using LangChain's expression language. Well, we have a lot of ground to cover, so let's get started with the Wikipedia tool, shall we? First things first, open your Anaconda prompt and activate the LangChain environment. Then, pip install the Wikipedia library necessary for working with their API. Once the installation is complete, open a fresh Jupyter notebook using that same environment as a kernel. Enter the familiar magic commands. The classes we need for this lesson include the following: prompt template and string output parser from LangChain Core, Chat OpenAI from LangChain OpenAI, and Wikipedia API wrapper and query run from LangChain Community. Next up, define a variable called Wikipedia API and assign it an instance of the Wikipedia API wrapper class. As the name suggests, this wrapper uses the Wikipedia API to fetch articles through the load method, or page summaries through the run method. Let's give the run method a try and pass a string of choice as an argument. I'll go with Python. Additionally, since the output of a run method is a string, I'll wrap the expression in a print function for nicer formatting. Very well, we obtained summaries of the Wikipedia pages for the Python programming language and the Monty Python comedy troupe. The next step is to use this API to create a corresponding tool. For that, we need to employ the Wikipedia query run class, inheriting the properties of the runnable class. Now create a new variable called Wikipedia tool and assign it to an instance of the named class. Set the required parameter, API wrapper, to equal Wikipedia API. Excellent! The parent class of Wikipedia query run, base tool, comes with two required parameters, name and description. We can access them through the dot notation, like so. The description sounds familiar, doesn't it? Additionally, we can apply dot arguments to display the familiar JSON input schema. All right, moving forward. Since tools are runnable objects by implementation, we can apply the invoke method to our Wikipedia tool to retrieve page summaries. From the input schema, we learned that it expects a query as an input, so let's map query to Python. Save the output in a variable called response. Pass the variable as an argument to a print function. We find the same two summaries about Python and Monty Python. For further convenience, note that we don't need to pass an entire dictionary when invoking the Wikipedia tool. A simple string containing the query would do, like so. Okay, finally, for this lesson, let's quickly demonstrate how to pipe a tool to a simple chain constructed from a prompt template, a chat model, and an output parser. For starters, let's use the following prompt template. The instructions read, turn the following user input into a Wikipedia search query. Don't answer the question. Next, define the familiar chat model. You can pause the lesson and copy the code to your notebook. Let's now create the chain. Start with the prompt template, continue with the chat model, and finally, pipe an instance of the string output parser class. Invoke the chain with the following input query. Who is the creator of the Python programming language? As instructed, the Chain's LLM has rephrased the question to make it suitable for a Wikipedia search. Let's now invoke the Wikipedia tool with this exact string. To do so, append the tool at the end of the chain and invoke it again. And there we have it. We've retrieved the relevant Wikipedia page. Excellent! In the following lesson, we'll define two more tools, one from a retriever object and another from a custom Python function. I'll see you shortly. Welcome back, everyone. In the last lesson, we constructed a tool that uses the Wikipedia API to retrieve page summaries based on a user's query. We found that tools in LangChain are runnable objects that can be used as the building blocks of chains. In this lesson, we'll create two more tools, one defined from a retriever and another from a custom Python function, which returns the version of Python used on the current platform. To achieve this, we need to import the following classes and functions: Chroma, OpenAI embeddings, tool, create retriever tool, and Python version. Feel free to pause the lesson and apply these imports. Let's start with the tool defined from a retriever object. Using the local database created in the previous section, initialize a new Chroma vector store object. As we've seen in previous lessons, we need to specify the embedding function parameter. Let's now create the retriever. We could do this by applying the asRetriever method. Set the search type to a maximal marginal relevance, then employ the search keyword arguments parameter to specify the number of retrieved documents and the lambda value. I'll go with 3 and 0.7 respectively. Here comes the most intriguing part: creating the tool. Define a variable called retriever tool and set it equal to the output of the create retriever tool function. This function comes with 3 required parameters: retriever, name, and description. The value of the first one is, of course, our retriever object. Next, let's give the tool an intuitive name. I'll go with Introduction to Data and Data Science Course Lectures. And finally, we need to provide the tool with a description. Let's apply the following string. For any questions regarding the Introduction to Data and Data Science course, you must use this tool. And there we have it. Let's display the object. We find it's an instance of LangChain's tool class and includes the name, description, and function we set. Additionally, it comes with a predefined argument schema suitable for a retriever tool. Go ahead and append .argument to the object's name. We find a JSON schema like the one used in the Wikipedia tool, but with the additional description that the input is a query to look up in a retriever. Now let's apply the invoke method to this tool with the following query. Could you list the programming languages a data scientist should know? The result from this statement will be a string, so I'll apply the print function immediately. As expected, we obtained the content of the 3 retrieved documents. So far, so good. Next up in our game plan, creating a tool from a custom Python function. Follow me and define a new function called getPythonVersion. Use type hints to indicate that the expected output is a string. Inside the function's body, return the output of the Python version function. Additionally, write the description for this tool as a docstring in the body. Let's go with useful for questions regarding the version of Python currently used. We must now apply the tool decorator imported earlier to convert this function to a tool. Recall that we encountered decorators earlier in this course, where we utilized the chain decorator to wrap a function inside a runnable lambda. Okay, let's run the cell and display the function. This time we've created an instance of LangChain's structured tool class, which implements the runnable interface and contains all required tool parameters. The name we give to our tool is, by default, the one we provide to the function. We can change it by adding parentheses next to the decorator and adding the name as a string. Indeed, it worked! Let's also apply .arguments to study the input schema. We retrieve an empty dictionary, which is expected because we don't require input for this tool. Well, let's give this tool a try, shall we? Invoke it with an empty dictionary. Very good! We're making significant progress. Now that we're familiar with how tools in LangChain are created, it's time we dealt with some agents. Recall that to create an agent, we need a prompt template, an LLM, and a list of tools. In the next lesson, we'll prepare these components and, more notably, learn how to employ the LangChain Hub to fetch predefined prompt templates. Can't wait to meet you in the next lesson. Hello everyone, and welcome back to this lesson, where we'll prepare all the components necessary for creating an agent. So far, we've created a list of 3 tools: Wikipedia, Retriever, and a custom tool. The definition of the chat model is the same one you've seen many times throughout this course. Regarding the template, however, we'll bring some flair and learn how to pull up a predefined template from the LangChain Hub. Let's begin. First, to use the LangChain Hub, we need to install the corresponding library. Open the Anaconda prompt, activate the LangChain environment, and pip install LangChain Hub. As usual, I've prepared a portion of the necessary code. First, I've set the OpenAI API key as an environment variable. Next, I've imported a couple of classes and functions, all of which should look familiar, except for the Hub module, which we'll use for the first time now. I've then created the following: the Wikipedia tool with the help of the Wikipedia API wrapper, the Retriever tool, fetching relevant documents from the Intro to Data and Data Science course, and the Custom tool, retrieving the version of Python currently used. These 3 tools are inserted into a list with an intuitive name. Finally, I've defined a Chat OpenAI instance. Let's now create the prompt template. Start by defining a new variable called Chat Prompt Template. Set it equal to hub.pull and pass the template's name as an argument. That is, Harrison Chase, nicknamed HWChase17, followed by OpenAI Tools Agent. Let's display the variable and examine it closely. There's a lot going on here, and I think we can all agree it's a bit difficult to read. Thankfully, the Chat Prompt Template class implements a convenient method called prettyprint. All right, much better. So there are 4 chat messages in the following order. A system message reading, "You are a helpful assistant." A message placeholder expecting a chat history input variable. A human message expecting input from the user, and one more messages placeholder expecting an agent scratchpad input variable. But the definition of the template stores more information, so I've formatted it for better readability. Let's take a closer look. First, agent scratchpad and input are stored in a parameter named input variables. Next, we see an input types parameter, which allows us to specify the accepted data types for each variable: AI message, human message, and the rest. Finally comes the messages parameter, which, as we've seen in previous lessons, accepts a list of chat messages. As expected, they are the same as the ones from the prettyprint. Note, however, that the chat history variable from the first placeholder is optional. This means we can use this prompt template for chatbots with and without memory. In this example, we'll implement the latter. As a final remark, note that you can discover all available LangChain templates on the following website. Here's the one we worked with. All right, everyone, I'll conclude the lesson here. We now have a list of tools, a chat model, and a chat prompt template to feed to our agent. We'll dedicate the next lesson to discussing the types of agents currently available in LangChain, as well as creating one in code. See you in a bit. Welcome back, everyone. In the last couple of lessons, we prepared the list of tools, the chat model, and the chat prompt template, components necessary for creating an agent. Now we're finally ready to make one ourselves. So roll up your sleeves and let's get to work. Return to the last lesson's notebook and tidy up the file by navigating to the bottom and removing all cells displaying the chat prompt template. Next, return to the beginning of the notebook, enter the second cell, and include the following line of code. From LangChain, .agents, import, create tool calling agent, and agent executor. Navigate to the kernel menu in the ribbon to restart the LangChain environment kernel and run all cells in order. Good. Proceed by creating an object called agent. Set it equal to create tool calling agent. This function comes with 3 required parameters: LLM, tools, and prompt. Their values should be the chat model, the list of tools, and the chat prompt template, respectively. Next up, we need to create an agent executor to carry out the agent's decisions. To do that, let's define a new variable called agent executor and set it equal to the class of the same name. This class requires 2 parameters: agent, which we'll set equal to the object we've just defined, and tools, set equal to the list of 3 tools. Let's include 2 more parameters: verbose and return intermediate steps, equal to true. Okay, it's time we put this agent executor to the test. Apply the invoke method, setting a dictionary's key to input, and its value to any question that requires using any of the tools in the list. I'll go with the following. Could you tell me the version of Python I'm currently using? Store the result in a variable called response and run the cell. Due to the verbose mode, additional log information is printed on the screen. We can see that the process involves entering a new agent executor chain. This suggests that agent executor is, in fact, a chain specifically suited to executing actions specified by an agent. The same log shows the function to call and the results from this call. The chat model then responds based on this result and the initial question. Great! Let's now check what the variable represents. It's a dictionary with 3 key value pairs. The first one, with key input, stores our question. The second one, with key output, keeps the model's reply. The third key value pair keeps the intermediate steps as a list of tuples. Since there's only one step, the list contains a single tuple. The first object inside is a tool agent action instance that keeps information such as, among others, the tool used and the tool input. The second object represents the result. Okay, let's test the agent executor with one more request. It asks for details on programming languages a data scientist should know and some info on their creators. This might take a moment, so I'll cut the recording to the interesting bit. The log is much longer now. Let's study it more closely. First, we enter a new agent executor chain invoking the retriever tool. The model has modified the initial question as a retriever query, namely, programming languages a data scientist should know. The 3 paragraphs we see in the log are the contents of the 3 retrieved documents. Next, this information is passed to the agent, which has then decided that the next appropriate step is to invoke the Wikipedia tool with the following query. The Wikipedia tool provides a summary of the first 3 pages. The same tool is then invoked with Python programming language, Java programming language, and Scala programming language. Finally, using this new information and the initial question, the chat model has structured a final response, listing the program languages a data scientist should know, according to the course, and cites their creators, which can be found on Wikipedia. A quick look at the response variable again finds a dictionary with the input, output, and all intermediate steps. All right, I think now is a good time to stop. Next, we'll explore the inner workings of agents by invoking them with different intermediate steps and studying the possible outcomes. I'm excited to meet you soon in our final lesson for the course. Welcome back, everyone! In the last lesson, we used a list of tools, a chat model, and a chat prompt template to create an agent and an agent executor. Recall that an agent's task was to decide how to solve a problem, while an agent executor handled their execution. In this lesson, we'll step back and pay closer attention to the agent and the objects it can return, an agent action, a list of agent actions, or an agent finish. With that said, let's jump right in. Start by opening the last lesson's notebook. Restart the kernel and run all cells in order. Once done, invoke the agent executor with the familiar request to retrieve the version of Python currently used and store the result in a variable called response. Displaying the variable, the familiar dictionary stores the user's question and the model's reply. Take a closer look at the third key value pair. We find it keeps the intermediate steps, which, if you remember, consists of the action chosen by the agent and the result of this action. More specifically, we find a tool agent action instance keeping the action, together with the result of this action, 3.10.10. Okay, everything should be familiar by now. We'll proceed by asking the same question, but we'll study the agent more closely this time. Do as follows. Return to the cell where we defined the agent and enter a new one below. Let's apply the invoke method on the agent, passing a dictionary as an argument. The first key value pair will be our input. Could you tell me the version of Python I'm currently using? The second required key, intermediate steps, expects a list. For now, leave the list empty, indicating no previous activity. Running the cell, we obtain a tool agent action object, specifying the first tool to execute, which is, unsurprisingly, get Python version. Note that this output doesn't keep the result from this action. We now aim to pass a set of intermediate steps to the agent and study its behavior. Since an intermediate step consists of an action and the corresponding result, let's use the information stored in the response variable. Adjust the code accordingly and execute the cell. Very interesting. This time we obtained an agent finish object storing the final response to the question. An agent finish indicates that no further actions need to be undertaken. So, to summarize, we first invoked the agent, passing a question and no intermediate steps. As a result, the agent suggested an action storing the necessary tool and tool input. We then invoked the agent again, this time passing the action it had previously suggested as an intermediate step, and the corresponding result. Consequently, the agent returned an agent finish object, storing the final reply. I hope you're starting to get a feel for how agents work. In the assignment following this lesson, you will perform the same steps, but this time applying our second question, asking for the programming languages a data scientist should know and their creators. I'm certain you'll find the example illuminating. The second task I've prepared requires you to create an expression language agent chain. Carefully follow the instructions in the notebook, and by the end, you should have a fully functioning custom chain. Note that the chain you create is the one entering LangChain's source code to implement the create tool calling agent function. How cool, right? And with that, it's time we conclude our LangChain journey and say our goodbyes. Thank you for coming on board with me and exploring this vast and exciting world of LangChain. I can't wait to see the incredible applications you build with your newly acquired knowledge. Have fun and keep on coding.